presenter of, I'm sure, interesting talk, Emanuele Tognelli. Emanuele got his master's degree in physics at the University of Pisa in 2008, and after, in 2015, he got the PhD in physics at the University of Pisa with the having as supervisor Scilla De Innocenti and Pierprada Moroni, working already on prime sequence stellar model. After that, he had several postdoc in Italy, at the University of Rome, Tor Vergata. Also, for 1 year, he was also postdoc in our observatory in 2016 or 17, I don't remember. And nowadays, he has a postdoctoral fellowship at the Institute of Physics of the Czech Academy of Science in Prague. So he's an expert on stellar evolution from a theoretical point of view, and particularly he has made several work concerning prime sequence stars. Okay, so please, Emanuele.
So thank you very much for your kind invitation. It's a pleasure to be here, and I want to thank Michele and Santi for the opportunity to talk about something related to my work. So I have to switch to the presentation. So I start to share the screen, and I'm going to lose everything, so I can see you, but I hope you can see me, and I hope you can also hear me.
Yes, it's okay.
It's okay, perfect. So today I would like to talk, it's an introductory talk actually, very basics, to give an idea of the problem that we have in stellar evolution, in theoretical stellar evolution, when you try to include problems and also solution actually, when you try to include the effect of protostellar accretion. So you want to try to model a star not starting from the Hayashi track, as usually done in stellar models, but try to start the computation from the very beginning, from the contraction of the cloud. So the idea is, why do we have to start from protostellar accretion? Well, there are several reasons, of course, theoretical, observational. We see disks around the young stars, Inti-Tauri objects, so very young stars. They have the disk from which they gain mass. There are some particular kind of variables, Furi stars, that are stars, young stars, that has a quick luminosity burst, and such burst can be explained by the presence of a radial infall of matter, a very intense radial infall of matter actually. And from a theoretical point of view, we know we have to construct a star, and the star has to born from a fragmentation first, and then a contraction of a cloud. You have gas, you have interstellar, you have matter that contracts and produces a star at the center. So it's interesting actually to follow this process of formation and see what happens when you try to include it in stellar models. This topic has been studied in several years actually. The first complete work, it's at the end of the 60s by Larson, where they studied the collapse of the cloud, and they tried to see if it's possible to match the final stages of evolution of these stars, these protostars, which is the end of the accretion phase, to the normal evolution of stars along the Hayashi track. But there are other studies that try to do something different, because this cloud collapse involves hydrodynamical simulation, so it's not a stellar evolutionary calculation actually. It's hydrodynamical simulation that follows the evolution of the cloud. Well, there is the possibility to include the accretion also in stellar code, in hydrostat, monodimensional evolutionary code. And this work has been done by Pallas Taylor mainly, but there are other works and other people, and nowadays it is coming out again, this problem, so there are a lot of recent works. So the outline of the talk is more or less divided in these three parts. The first part, I'm going to discuss a bit about the early accretion phase, the early protostellar accretion phase, when you form the protostellar core, and so the contraction of the cloud. Then I'm going to talk about the main accretion phase, which is the accretion from the moment when you have an hydrostatic core that is formed, and you have an hydrostatic structure that is gaining mass on it, and it is increasing in mass until you reach the prime sequence. And of course, it is interesting to see what kind of effect we expect from the inclusion of these processes in your models, because there are several parameters that, some are free parameters, some are parameters that can be adjusted, and depending on the parameter that you choose, the range of the parameter that you choose, you can obtain something that can agree or not with observation. So it's good to see if it's possible using photometry or other information, also surface abundances, to see if it's possible to constrain the parameter space. Okay, this is more or less the outline of the talk. So before going to the accretion phase, let me show you something that is a standard models. So here you have in gray standard tracks, prime sequence standard tracks that start from the Hayashi line, very bright objects. And the other lines, this line, horizontal line, not horizontal, almost vertical line, almost diagonal lines, sorry, are the isochrons. These just to have an idea of how observations, that are dots, squares, triangles, and so on, are placed in the Hertzsprung-Russell diagram, to have an idea. Well, this observation comes from very young object, stars, binary stars, stars in associations, star in clusters, in star-forming region. And you see that more or less, to have a rough estimation, you see that all the bulk of the object, especially let me say the top, because we are interested in reproducing at least the top of this envelope of observation, well, they are located close to the 1 megayear isochrons, more or less. This is important because we'll take this isochron as a reference to check if the models agree or not with the data. Okay, so remember that we need something that we need to produce models that after the accretion phase has to be or above or not too much below the 1 megayear isochrons. So let's start with the computation of some cloud collapse. As I said, the first complete work was performed by, the third complete analysis was performed by Larson. There are other works that essentially confirm what Larson found. And without entering the details, which are complicated, and yeah, I have only a very simple sketch of which are the main phases. Essentially, you start from a cloud, a spherical cloud. You have an hydrodynamical code to describe the contraction phase. You start from something that is very cold, 10 Kelvin, with very low densities. Okay, so in the first phase of contraction, you expect that the temperature doesn't increase because the density is so low that you are trying to assemble particles together, but these particles do not interact. Okay, so the temperature doesn't increase. You have an isothermal collapse. But then at some stage of this contraction, you increase the density, you start to form something that is denser in the center. You expect in the center to have large densities, and you form some kind of core. It's not an hydrostatic core, or at least it can be hydrostatic for a very small interval of time. But it's a core that is increasing in mass. You have a lot of, it's quite complicated to follow the evolution of this part because you can have the formation of shock that is moving up and down in the envelope and can reach the surface of this core. The shock is essentially the region where the matter settles on the central core. So it's not an hydrostatic core, but as the collapse proceeds, you first dissociate of the molecular hydrogen and you reach a temperature of something about 2000 Kelvin. But at the end of this stage, all the simulations predict that you form what is called the second Larson core, which is an hydrostatic core. And the characteristic of this core is that it continues to be hydrostatic during the whole protostellar accretion phase. So it's the first time that you have something that is similar to a star. It's a protostar, but something that is hydrostatic in hydrostatic condition. So it's this is good because we can hope to follow the evolution also in stellar codes using this core as a starting model, but we will discuss about this later. So first of all, let's try to see the characteristic of this Larson core. Well, Larson and other authors perform a lot of calculation, changing the characteristic of the cloud, changing the density, changing the temperature, changing the mass of the cloud to produce stars with different masses. And it seems, and also metallicity, because we try to see also, we try to produce this kind of calculation also for metal poor stars. Mostly are for solar metallicity stuff, but we try also for metal poor stars. So what we found is that the characteristic of this core are almost universal, let me say, in the sense that even if you change a lot the initial condition of your cloud, well, you don't have such a large variation on the formation of this core. And this core has a mass that ranges between 1 and, this depends a bit on the author, but let's say 10, 13 Jupiter masses, 30 Jupiter masses, more or less, with a radius that can be between 1/2 and 5.7 solar radius. And the central temperature, as you see, it's quite low. So you have something that is burning nothing. There are no nuclear burning in these objects because they are very cold, 10 to the 4, maximum 10 to the 5 Kelvin. So it's an hydrostatic core with these characteristics that we can predict. Good. So what happens is that we have this core, the evolution goes on, matter continues to follow this core, the accretion rate depends on the model. In this kind of hydrodynamical simulation, you assume that you have a spherical accretion. So the star, the protostar, the core inside the cloud is interested by the accretion on its whole surface. Okay, so he has no possibility to radiate the energy away. So all the energy radiated in some particular phases of this accretion is trapped and is carried inside the star actually. Okay? These are details, but what is important is that you have the star that is deeply embedded into this cloud from the beginning to the end of the accretion. Okay, so we have the spherical accretion. Well, what you see from this simulation, if you try to compute different values of the mass, and here it is the sequence, which is called the Bert line. The Bert line essentially is the locus where you have the protostar that have reached the final values of its mass. So without the accretion has ended. You can create a line with different values of the final mass, and you create this Bert line. And you see that this Bert line is very close to the standard 1 megayear isochrones. This is good because if you look also in this small picture here, it's the same picture that I showed at the very beginning. You see that in this region you expect to have more stars. And what we want to do is to create models that are capable of reproducing the stars that we observe. So we need models that at the end of the accretion can reproduce the star that we observe, because the star that we observe has no accretion. So they ended the accretion phase. So at the end of the accretion, we want to reproduce those stars. And these models seems to agree with observation. Fantastic, because if you now switch to standard evolution, starting from this point, and Larzo performed also this calculation, you see that you have exactly the same evolution as standard model. You evolve along the Architrack, then you move in the any part, if you have a star that develops a radiative core, and so on. The normal evolution is saved. But there are some pros and some cons in this kind of analysis. So the pros, of course, are that you have constructed a detailed and consistent model to follow the evolution from the cloud collapse until you form the star. You have reached the final values of the mass, so to the end of the accretion phase. And you can consistently evaluate all the characteristics of the accretion. So you can evaluate the accretion rate because you are treating simultaneously the evolution of the core and the envelope. The core is essentially the star that is rising in mass. The core is the region where that supplies the matter to the star, so the region that determines the accretion rate. But also the accretion energy, everything is coupled and everything can be solved simultaneously. You don't have a lot of free answers. You don't have free parameters in this model. But the only free parameters are the geometry that you assume and the initial conditions. The cons are that you require aerodynamical calculations that are extremely hard from the computational point of view, so it's hard to produce a lot of models, and if you want to produce a stellar population to compare with data, you need a lot of models, as you probably know, and it requires a long interval of time to do that, okay? And then there is another problem that, in my opinion, it's most relevant, is a physical problem, in the sense that you see stars that at some stage develop an accretion disk. So you see that stars during the last evolutionary phases, and the last accretion phases, they accrete matter from a disk. And from simulation, it seems that most of the stellar mass is gained during this disk accretion phase. So this accretion phase cannot be included in spherical accretion, where you assume that the star is invested by this accretion material anywhere in the space. So you have a radial accretion, not a disk accretion. So for this reason, probably it's better to try to do something different, okay? To include and to treat in models this kind of disk accretion. So let's try to jump to the main accretion phase. Why the main accretion phase? Well, we know that the first part of evolution, when you have a cloud collapse, is hydrodynamical and you need spherical accretion. So you cannot treat that phase in monodimensional hydrostatic codes. Okay, so one can ask, is it possible to skip this phase and go directly to the main accretion phase when I have an hydrostatic core? Yes, we can do that. We can do that because Larson computation showed that there is a core, the second Larson core, that satisfies the requirements of hydrostatic condition. It is in hydrostatic equilibrium and it remains in hydrostatic equilibrium. So you can use that result from detailed spherical calculation from cloud collapse to start the calculation of your hydrostatic codes. And we know the characteristic of the Larson code. Here there is a brief summary of the characteristic: mass, radius, and temperature. So we can use this model as a first model, as a starting model. Good, but it's not sufficient because we need something more. We need to understand what kind of accretion do we want. Do we want an accretion scenario in which the star is deeply inside the cloud, and so spherical accretion? So again, we are in the case of hydrodynamical simulation, exactly the same results. Or do we want a star that is surrounded by an accretion disk that can be thin, can be thick? The important is that you have a disk, and the accretion occurs only on a limited part of the star. And this choice is very important and affects your results. So we want to study what happens if we use an accretion that assume a disk accretion. Here it is a snapshot of what we expect. This has been extracted from a very good review of accretion phases by Hartmann in 2016, I guess. I didn't put it here, but it's Hartmann 2016. So the idea is that you have a protostar in the center of this disk, a disk around this protostar, and some streams along which the matter falls on the stars. The assumption is that most of the surface of the star is free to radiate energy. So you have only this limited portion of the stars here where you put material. Okay? So you can essentially assume that your star is a normal star. You can follow evolution as a normal star in the hydrostatic core. We have to introduce some differences. So the basic equation that determines the stellar structure changes, but mostly of the code that you have to treat hydrostatic evolution of stars can be used. Okay, so this is essentially the assumption that we have. Now, what is important is that in this case, you cannot predict the accretion rate. You cannot predict how much energy you are carrying from the last stable orbit on the disk to the star, because you don't have the disk coupled to the star. So you follow all of the evolution of the star, and the characteristic of the accretion comes as external free parameters. So you don't solve simultaneously the structure of the star and the structure of the disk. You cannot have an idea of the accretion rate. So you have to adopt some values. They can be constant, can be dependent on the age, can be very complicated. Now, before going on, I think that it's useful to have an idea of what one can expect from the accretion of this protostar. In 1997, Hartmann adopted a very simple approach. He tried to model the accretion using analytical model, a polytron for a star. And this is what the equation that he obtained. The radius variation in time is given by this quantity. You have some classical term. Classical means that this part here does not include the accretion. You have the luminosity of the star, which contributes as a negative sign because you are losing energy at the stellar surface, you are radiating energy, so this will lead to a contraction. During the Premen sequence, along the Hashi track, you have the contraction. Then there is a term that comes from the energy generation, and in particular the deuterium burning, because remember, this is for protostars, so we are interested in the evolution of the Premen sequence. The only element that you can destroy is deuterium. It is positive because it produces energy. But you have also a part that is non-standard and depends on the accretion. Here it is the mass variation in time, which is the accretion rate, and you see that depending on the number, this number here, this term can be positive or negative. Okay? If you have enough accretion energy, and the accretion energy is defined this way, the accretion energy essentially is the energy, the thermal energy that the matter that falls on the star carry inside the star. If for some reason you have a kind of shock on the surface of the star, or a little before the surface of the, slightly before the surface of the star, in this shock it's possible that the energy is radiated away, and probably part of the energy is not going to reach the star. So you are adding no energy to the star. In this case, that can be simulated assuming alpha equal to 0, we call this case cold accretion because the material hits the star without internal energy, so it's cold with material. The opposite case is where you have that all the energy is retained by the falling matter, you add the maximum thermal energy possible, and this is called hot accretion. Of course, there are all the possible cases between 0 and 1, and depending on this value, you can have something that is similar to cold accretion or something that is similar to hot accretion. Now, just to start, let's focus on the case where alpha is equal to 0, which means cold accretion. I accrete matter, but the internal energy is very low compared to the internal energy of the star, so you are creating no energy. Well, from this equation, you see that this term is negative, because alpha equal to 0, so this term is minus something proportional to the accretion rate. And consequently, this term contributes to make the star smaller. We have a radius shrink. This is what we have if we try to perform detailed calculation. So that was an analytical calculation. This line here is the evolution of an accreting object using a detailed evolutionary code. Okay? In the case of cold accretion. So let's see what we have here. Normal standard evolutionary tracks, an approximate 1 megayear isochrons, and the accretion sequence. You start from the second Larson core and you gain mass, and you have this feature here. So this first part here, you see you have a contraction of the radius shrink. Why? Because we have this term that together with luminosity radiation at the stellar surface produces a radius decrease. The star decreases in mass, in radius, so the central temperature increases. Remember that the central temperature is proportional to the mass divided by the radius of the star. There is also the mean molecular weight, but in this case it's constant. So it's not important. If you reduce the radius of the star, you increase the temperature of the star. And once you reach the temperature of 1 megakelvin, you ignite the deuterium burning. So when you reach this point here, you have an expansion because you are producing energy. So this term in a Hartmann equation is positive. But as long as you continue to increase the mass of the stars, deuterium is not capable of maintaining the structure stable, or let's say expands, and so the stars at some point begin to contract again. And so you see that you go in this direction, and this is the last point that forms one solar mass star. So here you have one solar mass star that comes from the inclusion of protostellar accretion. Now compare this point here to one of these points along this track. Because here, more or less, you have an age of 10 to the 5 years, so smaller than 1 megayear, and you have a huge difference in luminosity and in temperature. So the problem with this kind of accretion is that for some values of the mass, you are not capable of producing the normal Freeman sequence evolution. And this is a problem because, as I said, we see data in this point here. So we cannot reproduce data of real stars. We can reproduce some data from this point and for lower masses. So let's say something below 0.2, 0.1 solar masses. This is a problem. The problem is even worse because I said that we have a range of values for the characteristic of the second Larson core. If we decrease the mass of the Larson core, these models is obtained using 10 Jupiter masses, which is a good value to start for the Larson core, but it can be smaller. And if you reduce it to some other value that is still fully compatible with the simulations, you see that the situation is even worse. And what you see is that for some values of the mass, about 0.6 solar mass, you ignite the hydrogen in the center, not the deuterium. You ignite the CNO cycles because you reach temperature above 10 to the 7 Kelvin in the center before the end of the accretion phase. That's terrible. And you completely skip the Hayashi line, you completely miss all the region where you see stars. That's a problem. You can change all the parameters that you want, the accretion rate, the initial radius. You can't reproduce the observed stars. But we can try to work a bit with other parameters. Remember, we can expand the stars if we use enough energy produced during the deuterium burning. And how can we increase the energy production in deuterium burning? Increasing the deuterium abundance. we measure the deuterium abundance. We know that there is a slightly uncertainty of the current value of the deuterium abundance. Let's see if we try to increase the deuterium abundance towards the upper limit, the upper observational limit, we can do something to improve the comparison. Actually, no. The result is that you need to reproduce more or less the region where the stars are observed, you need to increase the deuterium abundance to at least the value that you have during the Big Bang, predicted by the Big Bang nucleosynthesis. But we know that the interstellar value, the value of deuterium in the interstellar medium for population 1 star is much lower, is about 1/2 of that value. And again, you have a problem because if you change the initial model, it's not enough to use the primordial deuterium abundance, but you need something more. Here, for example, I plotted a completely unrealistic value, but I said, what value of deuterium do you need to match the evolution, the normal evolution close to the deuterium bounding region, that is these magenta lines? Well, you need at least an order of magnitude, the deuterium abundance to be 1 order of magnitude larger than what you see, and that's impossible. So, also deuterium cannot restore the agreement between models and data if you assume cold disk accretion. So, go on. There is another possibility, and it's the possibility of including some level of accretion energy here, because for the moment we assume that this term is equal to 0. But if this term is larger than 1/7, which is a critical value, this term becomes positive. If it's smaller, it is negative. So this value of alpha 1/7 is more or less a transition value between what we call cold accretion, because if it's smaller, this term is negative and it contributes to the contraction of the star, or hot accretion if this term is larger, and so this has a positive contribution, and there is a possibility to increase the radius of the star. So what we can do is try to see what happens if I adopt a value of alpha that produce hot accretion. So the matter falls on the star, on the protostar, with a not negligible content of internal energy. So here is the result of this simulation. These figures are taken from Kunitomo and they adopt a different definition. Instead of using alpha, they use the value of key. But it's the same, so you see that this means alpha equals 0.5. So in the radius and in the Hertzsprung-Russell diagram, it's better to see what happens in the radius. This almost invisible line here corresponds to the case of cold accretion, or purely cold accretion. You have no energy added, and you see that the radius shrink. So you have no possibility to reproduce the data. The black line here is the standard model for one solar mass. I forgot to say, this is the result for one solar mass star. So this is the standard evolution in the Riemann sequence. Now, if you increase the content of internal energy in the accreted matter, you see that you increase the radius. And especially if you use what is called the really hot accretion model, you see that the radius increases very quickly during the protostar accretion. It reaches the maximum values when the accretion ends, and from the moment on, it relaxes to the normal evolution. Now, the time that it requires to relax to the normal evolution is more or less a Kelvin-Helmholtz time scale, which is of the order 10 to the 5, 10 to the 6 here. But from the moment on, you fall exactly on the evolution of a normal standard Riemann sequence star, okay? And you see in the Hertzsprung-Russell what happens. So now I don't have the isochrone of 1 megayear, but more or less the isochrone of 1 megayear is this one, pass this way. So you see that you can produce models that are more luminous than 1 megayears isochrone. And that's good because I can produce models at the top of the Hayashi line of standard evolutionary tracks that then evolving goes down and can match the data. What is important is that if you change the initial mass, sorry, let me go back again, these assume a 10 Jupiter mass Larson core, okay? But if you decrease the mass, you obtain the same result. So these are different accretion sequence with different value of the Larson mass. The black one is 10 Jupiter masses, the blue one is 5 Jupiter masses, so 1/2, and the red one is 2 Jupiter masses. Now for the red one, I also changed the accretion energy. But what is important is that, for example, in the blue and the black lines, after an initial phase where they are different, sometimes to relax, they are exactly the same. So they rapidly converge. Why? Because this term acts as a feedback. If the radius of your star is too small, the accretion energy is large. So you accrete more energy on the star, which reacts expanding. If radius expands, the accretion energy decreases, and so again the radius starts to contract. So you have a counterbalance feedback, but a negative feedback of this situation that produces a stable star, and so a stable birth-line or sequence or accreting sequence. If you decrease the value of alpha ACC, you have a slightly fainter accretion sequence, but again, it's something that is very luminous and above the region where we see data. So it seems that hot models are good candidates to produce what we want, to produce stars starting from the protostellar accretion that ends very close to the accretion phase very close to the Hayashi line. And so from that moment on, essentially what you have is a normal evolution. Okay, and you can reproduce also the data. So I put everything together in this slide to have a direct comparison of the models. For the hot accretion case, you can produce any mass you want, at least in this mass range. I stopped to one solar mass. If you go above one solar mass, there is something different, but I don't want to talk about that because I'm interested in normal stars. It is interesting, but it deserves another seminar to talk about that. However, in hot accretion, you can produce all the stars that you want. In cold accretion, you have problems. You have problems that depends on your initial model. So there is a region that is very bad. You cannot reproduce anything in that region. There is a region where you can reproduce something. And that region more or less corresponds to 0.1, 0.2 solar mass, and depends. So the question is, do we really need hot models to form any Luma stars? We don't know. We don't know actually, because cold models could work also for very Luma stars. For sure, they do not work for a larger star. But for something about of the order of 0.1 solar mass, yes, probably they work. So the maximum that we can extract from this comparison of the Hertz from Russell is this kind of limit for cold or hot accretion. But as I said, the real accretion phase the protostellar accretion phase is more complicated, because you have an initial phase where you have this spherical accretion, where the matter is trapped, the radiation is trapped inside the envelope that is collapsing. So it's something that is similar to hot accretion. Then at some stages you switch to a disk accretion because the cloud collapses to this disk. And in disk accretion, if you have no large accretion rate, probably the accretion is more likely to be cold. So a simple example exercise, let's say, could be to try to simulate this scenario, assuming first an hot accretion, disk hot accretion, so you set the parameter of alpha equal to 1 or whatever, and then at some values of the mass you switch to cold disk accretion. This work has been done by Hosokawa, and you see that this is the hot sequence for any mass, of course, until you reach the 1 solar mass here. You start for the Larson core and you evolve in hot accretion. Then you can take one of these models here and say, okay, at this value of the mass, I switch to cold accretion. No, I want to switch to cold accretion at this value of the mass. Or no, I want to switch to cold accretion on this value of the mass. And compare the results to purely cold accretion case, where you start the protostellar evolution assuming cold accretion for any value from the very beginning. And you see that the radius is very different. So it's enough, also in the Russell diagram you see the same, that you see that these models here are the models of cold accretion. Remember, this model has been computed for 10 Jupiter masses. If you reduce it to 1 or 2 Jupiter masses, you get something that is very below here, close to the 10 megayear isocross. So you skip all these observations here. So this depends on the mass. On the other hand, the hot line does not depend on the mass. But what is important is that if you switch to cold accretion, you have a possibility to produce something that is still in agreement with the data. And these tracks here, okay? So these tracks here are tracks where you have switched to cold accretion. Well, This is very interesting because it's something that this model it's a bit more close to what we expect can happen in real forming regions. A phase of hot accretion followed by a phase of cold accretion. And in particular, this model here, you assume that if you want to form one solar mass stars, you assume that you gain most of your mass, if not all the mass, in a cold accretion scenario. So this model here that reproduces the observation is the model where you say, I accrete in hot accretion scenario only for a limited interval of time, and then following the suggestion of these scenarios, I gain most of the mass of the star in a cold accretion scenario. However, you have a star that is expansive, that is large enough and bright. Now, we can do even something better, as it has been done. Why don't we try to couple stellar evolution model to disk models? Or why do we don't try to semi-couple? Now I'm going to say why semi-couple. This has been done by Baraf, Forbio, and Chabri. They try to take the results of real, let me say, disk simulations. So you have a code that treats the evolution of a disk in time, of a accretion disk in time, and at the center you put a star and follow the evolution of this star. You put a protostar, a protostar, and follow the evolution of this protostar, assuming the accretion rate that comes out of this disk model. Why semi-coupled? Because as far as I understood, they do not have a feedback of the luminosity of the star on the disk structure. So they have a disk that evolves in time without an accreting protostar in the center. They assume some gravitational potential with a star that has a mass equal to the one that you want to produce, but you don't have the feedback of the radiation of the star that can change during the accretion phase. On the other hand, so after these computations, they take the results of this disk and the accretion rate and use these to evolve a protostar in an evolutionary model. But what you see is that the accretion rate in a real disk model is far from being constant. It's something that is very complicated. It's a forest of hills and valleys. You have a mean accretion rate of the order of 10 to the minus 6 that tends to decline in time. And that is what you expect in disks and what you see also in real disks. But when you have these peaks, the accretion can reach values as large as 10 to the minus 5, 10 to the minus 4, even 10 to the minus 3. So you have this strong burst of accretion. Well, let's try to see what happens if I take this accretion rate and put it into a model. Assuming different value of the accretion energy. First, we assume that the accretion energy is equal to 0. And so this is the evolutionary path of the cold accretion star. And as usual, you produce something that is very faint and cannot reproduce the data. Then let's try to see what happens if we increase the value of the accretion energy passing from 0.02, 0.04, 0.2, and they stopped. Actually, you can go a bit larger into 0.5 should be a good value probably. However, but not for this value is being adopted not for the all values of the accretion rate, but they put a threshold of 10 to the minus 5. They say if the accretion rate overcomes 10 to the minus 5, we assume hot accretion. If the accretion rate is below 10 to the minus 5, well, we assume cold accretion. Why? Because they estimate, it's a very simple calculation, they said that in a disk model, probably 10 to the minus 5 corresponds to a transition between a simple model where the matter falls on the stars and radiates its energy because you're not accreting the matter very fast, to another regime in which the matter is pushed towards the star for accretion rate of the order 10 to the minus 5 or 10 to the minus 4, is pushed to the star, and even if it radiates some energy, the column of matter behind the shock front, above the shock front, trap the radiation at some level you are capable of pushing this radiation inside the star. So we put this pressure, 10 to the minus 5. And you see that you can produce data because you are in this region, close to this is more or less the isochronal 10 to 1 mega year. So you can reproduce the data for a final mass of 0.75 solar mass. If you increase a bit this number, of course, you have a model that is brighter. So there is the possibility to do that. And this is just a figure that reassumes what I said. If you run the simulation for different values of the mass, you see that only in the cases with triangles, only in the cases where you have hot accretion models, in these, only for mass accretion above 10 to the minus 5, you can reproduce the data because you have a larger radius increase, here it is reduced, and everything is good and everything is saved. So this is a more realistic model. But let's try to see, because so far we have tried to see if it's possible to do that in using only photometry, but what happens in the case of lithium, for example? Because we know that lithium is can be a friend or it can be an enemy, because it is very sensitive to the temperature, so it tells you what happens during the protostellar or the primary sequence evolution, and so having an idea of its abundance and how the abundance changes in time compared to the data can tell you some information about what happened to the star. So here's a plot where I show the observation. We have a lot of data here. Younger clusters, not so young clusters, binary stars, a lot of stars, a lot of observations. But what you see is that you have a trend. For very young objects of the order of some mega years, you have no lithium burning. You do not observe a lithium burning, a lithium depletion. But if you increase the age, you see a depletion of lithium. Good. So similar to what we've done before, let's say that this isochron, 50 megahertz, corresponds to the bottom of this envelope where I see data, and see what happens in stars with the accretion. I'm reaching the end, 2 more slides and then we finish. So here it is a plot that shows the temperature at the bottom of convective envelope. Actually, during the protostellar evolution, the stars are fully convective, so this is exactly the same as the central temperature. And there are standard models, as usual, in gray. The magenta line indicates the region where you have deuterium burning. As you see that you have a flattened temperature, because when you ignite deuterium, you know that you have a sort of thermostat effect that prevents for a temperature increase. But it's not important, just a curiosity. However, this is the evolution of an accretive model in cold case, in cold accretion, with a normal accretion rate of 10 to the minus 5. And you see that you have a temperature that rapidly is increasing, and for more or less, I don't remember exactly, I guess it's 0.2 solar mass, you overcome the threshold at which lithium is destroyed. So you started to deplete lithium, and the temperature is still rising very fast. So the rate at which you deplete lithium is so fast that even if you are supplying lithium to the stars, because you are creating matter, so you are putting fresh lithium on the star, but the depletion rate is very fast and all the lithium is destroyed. Here it is the evolution in time of lithium. So you start to deplete lithium and boom, immediately you destroy all the lithium for masses above 0.2 solar mass. So above 2 solar, 0.2 solar mass. So for objects of more than 2.2 solar mass, you should see no lithium for any age here, because for here you have an age more than 10 to the 5. So 1 million year, 2 million years, you see no lithium. And this is contradiction with what you see in data. We see in a moment. If you assume hot accretion, on the other hand, the temperature never reaches the lithium burning threshold temperature. You stay on temperature of the order of less than 10 to the 6 Kelvin. So you can barely reach the ignition of deuterium, but very softly. So you never burn lithium during the protostellar phase, and indeed the evolution of lithium is something that is constant until you reach your final value of the mass. So here it is exactly the same, but I want to show these 3 models, hot accretion models, cold accretion models with a large Larson core, cold accretion model with a small Larson core. So you see that in hot accretion models, you have lithium preserved during the evolution. During the evolution along the line, which means during the protostellar evolution. Cold accretion, well, you start to burn lithium, but if you reduce the mass, the burning of lithium occurs faster and faster and at younger ages. And the problem, as I said, is that you cannot produce lithium, you cannot preserve lithium in stars massive or massive than 0.2 solar mass. This occurs not only in solar mass stars, but for any values of metallicity. We also checked it in with a paper with Santi and Maurizio, where we tried to see the impact of protostellar accretion on lithium in low metal pool stars. And we have the same result. If you adopt cold models, it's very hard to reproduce the observed lithium. Here it is the comparison in the observational plane, where you have lithium versus temperature. And as I said, the shaded area represents where you expect to have data. The other lines are the gray, the dark gray are the standard models. The colored lines are hot models with different ages. And you see that in hot models, more or less, you reproduce what you expect in standard evolution. Because, as I said, you can put a star at the end of the protostellar accretion phase at the top of the Ashley line. So the evolution is almost. But for cold accretion case, it's different, completely different. For any age, you have for any value of age, you have this rapid depletion of lithium. And you can partially reproduce the cold side of this lithium pattern, but you cannot reproduce the hotter part of the lithium pattern. Well, you expect that the largest stars are of the order of 1 solar mass at these ages preserve their initial lithium. In models with protostellar accretion and cold protostellar accretion models, you cannot produce stars that have lithium if the mass is larger than 0.2. So that's the problem. Okay? And so we reach the end, just a summary to show you that, just to summarize everything, so it's possible to include the accretion phase in models. Fantastic. There are several possibilities. We can include it in accretion, in spherical accretion, or disk accretion. Probably it's better to have the description in disk accretion because it seems to be more reliable. The problem is that you have some free parameters that you have to set. Okay? And depending on these free parameters, you have a set of models that are in agreement or not with data. Okay? Generally, what we see is that hot accretion models produce the best agreement of the whole evolution. Okay? And then, it is the last slide. I left you with this slide. You can also try to apply at least part of the every number seminar. You can also try to apply the accretion to produce clinically peculiar stars, young stars. They are observed in clusters, or also try to use some bees to produce second generation stars in globular clusters. You can use the accretion of matter with different chemical composition to produce the anomalies. So let's say that it's finished, it's the end, and I switch probably to the